It started with a faint hiss. A man sitting on a flight from Louisville to Baltimore looked down, confused. His brand new phone, a Samsung Galaxy Note 7, was smoking. Within seconds, the seat beneath him began to melt. Passengers screamed as a thin trail of white vapor turned into a burst of orange flame. The cabin filled with the sharp metallic smell of burning chemicals. Flight attendants rushed in with extinguishers while others evacuated the plane. The explosion was over in less than a minute, but that single minute would shake the entire tech world. In August 2016, reports began to multiply. Phones catching fire in living rooms, cars, pockets. One video showed a Note 7 igniting on a nightstand, setting an entire bedroom ablaze. Another captured a phone bursting into flames while charging on a desk, sparks flying like a miniature flare. By October, 112 confirmed battery fires had been recorded across the world. Airlines began banning the device from flights. Samsung issued a global recall, over 2.5 million phones. And yet, even some of the replacement models caught fire. In total, it cost Samsung more than $5 billion and scarred one of the most advanced technology brands in history. But beneath the headlines and lawsuits was a deeper, more unsettling question. How could something so small, something we carry in our pockets every day, be so violently unstable? The answer lay in a silvery, lightweight metal, lithium. Lithium, symbol Li, atomic number 3. It's the lightest metal on Earth, so light it can float on water. But when it touches that water, it doesn't just float, it explodes. Lithium reacts with moisture in the air, forming hydrogen gas and heat so rapidly that the gas ignites instantly. What's left is a fierce, crackling flame that burns bright crimson. This is the paradox of lithium, a material so dangerous it must be stored in oil or inert gas, yet so essential that nearly every phone, laptop, and electric car on Earth depends on it. Inside your smartphone, lithium atoms sit trapped inside a wafer-thin battery cell. When you charge the phone, lithium ions flow back and forth between electrodes like tiny commuters. That motion, controlled and balanced, powers our lives. But disturb that balance, a puncture, overheating, or even a slight defect, and lithium's wild nature returns. The battery short circuits, temperatures spike above 500 degrees Celsius, and oxygen from the electrolyte feeds a self-sustaining chemical fire. That's what happened in the Galaxy Note 7. Microscopic manufacturing flaws caused electrodes to fold and press against each other. A few atoms misplaced, and the entire energy of a battery condensed into a chain reaction of heat, gas, and flame. It wasn't just a phone that burned. It was a glimpse into the volatile heart of our electrified civilization. Lithium wasn't always the metal of smartphones. It was first isolated in 1817 by Swedish chemist Johann August Arfwedson. For more than a century, it sat quietly in labs, a curiosity of the periodic table. But during the Cold War, lithium gained a darker fame. In the 1950s, the U.S. military discovered that lithium deuteride could fuel thermonuclear weapons. The hydrogen bomb, the most powerful weapon ever built, literally depended on lithium. In 1954, the Castle Bravo test released energy equivalent to 15 megatons of TNT, 3 times more powerful than expected, due to an underestimated reaction with lithium isotopes. Entire atolls vanished. Thousands were exposed to radiation. So yes, the same element that powers your phone once powered nuclear annihilation. Yet, by the 1970s, scientists began to see lithium's gentler potential. They found that when used in batteries, its lightweight structure could hold incredible amounts of energy. In 1991, Sony released the first commercial lithium-ion battery, and the world changed forever. Today, that same chemistry fuels over 16 billion mobile devices, 30 million electric cars, and a renewable energy market projected to exceed $700 billion by 2030. But progress always casts a shadow. Most of the world's lithium, more than 70%, is mined in what's called the lithium triangle, the salt flats of Chile, Argentina, and Bolivia. In Chile's Salar de Atacama, extracting a single ton of lithium requires 2 million liters of water. That's enough to sustain 10,000 people for a month, drained from one of the driest regions on Earth. Communities there watch their rivers vanish and their crops fail as evaporation ponds stretch to the horizon, shimmering turquoise and toxic. The air grows thick with dust and chemical residues. One local farmer said, "It's like they're drinking our future." Meanwhile, in other parts of the world, lithium extraction leaves behind toxic brines that seep into groundwater, affecting both animals and humans. And yet, global demand keeps rising, expected to quadruple by 2035 as we push toward electric vehicles and clean energy. Lithium is at once our savior and our burden, the element that might save the planet from fossil fuels, but threaten entire ecosystems in the process. Every year, more than 25,000 lithium battery fires are reported globally, from electric scooters to power banks, from recycling centers to homes. In 2022, a recycling plant in New Jersey caught fire when a crushed battery triggered a chain reaction. It took 9 hours and thousands of gallons of water to contain the blaze. Firefighters describe these incidents as almost living fires, unpredictable, reigniting days later, because the lithium keeps reacting deep inside. One fire chief put it simply, "You can't extinguish lithium. You can only wait until it's done burning." That's the terrifying beauty of this metal. Once it wakes, it refuses to sleep. Scientists across the globe are racing to make lithium safer. Solid-state batteries replace flammable liquid electrolytes with stable ceramic or polymer layers, drastically reducing fire risk. Companies like Toyota, QuantumScape, and CATL have invested billions in this next-generation design. In laboratories, researchers experiment with nanostructured lithium anodes that could double energy density, meaning smaller, lighter, longer-lasting batteries. And recycling technologies are emerging, recovering up to 95% of lithium from old batteries, a process once thought impossible. Yet, each advancement brings new challenges: cost, scalability, and, above all, the environmental toll of endless extraction. As we look to the future, scientists are exploring sodium-ion, magnesium, and even solid carbon-based batteries. Sodium, abundant and cheap, could someday replace lithium in stationary energy storage, but it's heavier and less efficient. Magnesium promises twice the energy per volume, but remains unstable in air. Still, the question isn't just what comes next, but how we use what we already have. Imagine a world where every discarded battery is recycled, every car powered by clean grids, every device designed for circular use. We might reduce lithium's curse, not by replacing it, but by respecting it. At the core, lithium's story is our story. It's the story of a species that dares to harness lightning, to bottle fire, and call it progress. Every phone call, every video watched, every heartbeat monitored on a smartwatch is powered by this paradox. A dangerous, reactive element tamed into obedience, but every advance carries risk. Every spark the memory of what happens when control slips. In the 2016 Note 7 crisis, millions returned their phones out of fear. Yet, just a few months later, new models emerged, thinner, faster, more powerful, powered by the same volatile chemistry. We learned, we moved on, we kept charging. Maybe that's the essence of humanity, not the elimination of danger, but the will to understand it. Lithium reminds us that power always comes with a cost, and that knowledge, not fear, is what keeps that power alive. So the next time your phone warms in your pocket or your car hums silently down the road, remember, you're holding lightning and trusting it not to strike. Yet we continue to push the boundaries of this paradox. Right now, the world consumes over 180,000 tons of lithium every year, and that number is expected to exceed 500,000 tons by 2035. A single data center powering your searches, your cloud memories, can use up to 100 megawatts of energy, enough to power 80,000 homes, and most rely on lithium backup systems to never lose a second. We have built a civilization so electrified that a 30-minute power outage in a major city can cost millions of dollars and affect hundreds of thousands of people. Still, lithium keeps flowing through our veins of technology, silently, dangerously, beautifully. In space, the International Space Station depends on 48 lithium-ion battery units to survive each orbit of sunlight and darkness. Even 400 kilometers above Earth, we trust this volatile element with human life. So we charge, we upgrade, we innovate, knowing the risks, accepting the cost, because progress was never about safety. It was about daring the lightning to strike and using it to light our way.